agriculture, but also restoration. Strategy here is called rainwater harvesting structures. One example is the Demi-lunes. So Demi-lunes, they are just the semicircular earth embankment. Try to the purpose is to stop the rain, collect the rain runoff and increasing the water infiltration time, and then capture the moisture during the rain seasons. So the vegetation can use those extra moisture to grow up more quickly. These structures are relatively low cost, but very hard to measure. So here comes a very important question: is that how can we rigorously evaluate whether those stimulus actually improve the ecological conditions? So imagine you're a researcher, try to evaluate those stimulus structures. What variables you think can be very useful to collect? So for example, we can collect some soil samples to get the soil moistures, or we can collect some crop yield to assess whether those crops are improved by the stimulus, right? But all those measurements, they are collected at a plot levels. So most existing studies rely on plot level collections. And then those studies have some limitations. For example, they covered limited spatial extents, have relatively smaller sample size, and may not capture the long-term landscape dynamics, right? And then that is where the geospatial impact evaluation can help a lot here. Using the satellite images, we can observe a longer time period, but also can capture large geographic areas. So today's sessions will focus on these two learning objectives. The first of all, we'll know how to construct statistical comparable treatment and control group in a data scarce environment. Second, we will know how to design evaluation design to study the treatment that carry out at different times. What we call is the staggered rollout situations. So here is the workflow for the whole project. The workflow is divided into two parts. The first part is to getting the geospatial data, and the second part is the actual impact analysis. So today's workshop will primarily focus on the second part. The geospatial dataset will be provided later. You can download from the Google Drive folders. And but even though those datasets are provided, I will briefly introduce how we can get those geospatial datasets. So one challenges for this project is that we actually don't have the locations of those demos. So what we did is that we used the high resolution imageries. We digitize each demi-lunes on those images. Those demi-lunes, they are spatially clustered, and then also they can be easily identified by those half circular, semicircular shape. After we get the locations of each demi-lunes, all those demi-lunes, they are aggregated to grid levels. So those grids are used as the treated grid layer. And then also demi-lunes, they are not arbitrarily constructed. They're actually constructed perpendicular to the slope. So they will constructed on some specific locations. Therefore, to select the best comparable comparison cells, what we do is that we generated some grids within the 600 meters buffers around the clustered demi-lunes. In that way, by using this buffer constraint, we want to make sure they have kind of similar geographic characteristics such as elevations, slope, and as well as some weather climate characteristic like precipitations and temperature. So for the outcomes, we have the NDVI to monitor the vegetation greenness and health. We also have the soil moisture. The soil moisture indices is the NMDI. In this case, that is monitored for the dropness of the soils. So basically, if we see a higher NDVI, it's indicated the vegetation are greener. But like a lower NMDI is expected if there's more moisture in the soils. And those outcomes are calculated using the landside images. So let's dive into our hands-on sessions. So everyone can go to this link. Okay, here is the link. This link will lead you to the Google Drive folders contain the data set as well as the R Markdown file with the script we're gonna use later. So you can download the whole folders and then unzip it on your laptop. I will pause here for several minutes so everyone can download it on the laptop.
Is there anything we should have open to begin with, like the PDF or?
So you want to open the R Markdown file. This.
R Markdown.
Yeah, it's like and with the .rmd.
Yeah.
Yeah. So like in that file, you will see like lots of code chunks. So you can go to this link. You just tap the link. It will like lead you automatically to the folders. And then we will use these packages. So if you like the R Studios doesn't have the packages installed, you can like install the packages first. Is that too small? So it's like tinyurl.com and then 2026 GeoField database.
I think it was in the email that was sent from GeoField yesterday too.
Yeah.
I want to type it in.
No, but the email, I think there's problem that email was not actually people.
Oh, okay. The scanner.
No, it's fine, we just.
Rejected.
Okay,
Oh, no.
That's happened.
Yeah, I can't think of everything. This one.
Yeah, great. So then after
Can I ask? Just because I know what it takes. So you very quickly glossed over that you hand labeled 180,000.
right.
You could explain in 30 seconds what that took.
Oh yeah, of course. So like because we don't have the locations of Demi-lunes, so what we have to is that we just go to the images and try to zoom in really big and to see where those Demi-lunes are, and then we manually digitize each Demi-lune by placing a point at the on the central of each Demi-lune. So at the end, what we have is more than 180,000 points of Demi-lune. Yes.
You spent several weeks, right? Several weeks staring at Google Earth Pro, dropping points.
Several weeks, more than several weeks.
Well, like full time.
Yeah, full time.
Full time equivalent.
Yeah. Like well, while doing this, I'm also doing some other stuff. But like in general, after 3 months, we get the final digitized form. Yeah. Do you have a question?
Yeah, and so how do you know how did we get from around to like how did we get to know about the existence of these demilunes and like how did you like get infused? Like how did you know that you could see it from
actually
like images or you were actually doing some work for some other project and you just like zoomed into it and then you're like, oh, what are these circles? Or like semicircles and then you just like
I think the first idea is from we have a collaborator who works with those terminals before. So we have like a rough idea, like we know those terminals exist in these areas, but we don't know like where they actually locate. So that's why we went to those places using the high resolution Google Earth Pro images, so you can really see those terminals on those images. Yeah. So everyone good with the file, the script, and also the packages? Okay. So like those code are actually divided in big chunks, right? You can ignore the first chunk. It's just some like environment settings. But like let's move to the next chunk is to import all those required packages by using the library functions. So you can just click the little green arrow on the red corner of that code chunk, and that will run the whole code chunk. And then you can like use those packages. Let me know if you like run into some issues or questions. Yeah. Yeah.
About Demi-lune and but these are conceptually the same as what in Somalia they do is contour booms and which are they basically have water, etc. We can probably do the same. I mean,
Yeah, probably.
it's one but how do you replicate this study in Somalia, not Demi-lune, but the other thing that
Yeah, if like they kind of like work in the same purpose, probably it could be like carried out for the same whole analysis, right? Because I know like there are lots of other types of rainwater harvesting techniques. Yeah, it just capture runoff after the rain, right? The Demi-lunes is that they are kind of visible size from the images. They are usually 2 by 4 meters. So in that way we can digitize those. But like for the structure smaller than maybe meters, it's hard to identify them on the images if it's too small. Yeah. Okay. Are we good with the packages? Okay. I will move on to the next step. So like familiarizing ourselves with the data set before running the analysis is a significant step, right? So we can, in the folders you download, there are 2 CSV files. Those contains the data, the remote sensing indices for the treatment grid cells and the candidate comparison grid cells. And then we're gonna load those 2 data sets by using the read.csv functions. And then we can use the str function to inspect those data sets. So we can run the next code chunk. So in that way, it will like the result will give you a bunch of variables in those 2 data sets. And then here also the table summarizes what you will see in the variables. So like the NDVI mean and NMDI mean, those are the 2 outcomes we're gonna use later. And those outcomes is a mean value, is a seasonal mean values. For each year, the year is divided in 3 seasons. So in southern Niger, the rain season is in the middle of the year from June to September. So we divided the year into like dry period before the rain, and then the rain season, and also the dry season after the rain season. And then for each season, we calculated the NDVI mean and the NMDI mean as the outcomes. So after we have all those candidate comparison grid cells and the treated grid cells, what we want to do is that we want to find the most similar comparison cells we can use for later DID analysis. So in that way, what we are not matching using the magnitude. Actually, in this way, we matching based on the trajectories of the NDVI and NMDI, how it changes before the treatment. By doing that, we strengthen the plausibilities of parallel trend assumptions. So what is the parallel trend assumptions? So this assumption is that without any treatment, what we should expect to see is that the treatment areas are changed exactly on the same trend with the comparison trend. So that's why when we do the matchings, we want to look through each clusters, each like Demi-lune clusters, on each treatment timings, and then we calculated the pre-treatment NDVI and NMDI slope, and then we're gonna use those slope to find the best comparable comparison cells. So the mechanism, the algorithm we use here is we find the 5 most closest neighbors to the most similar comparison grid cells using the nearest neighbor matching algorithms. So we can run the whole matching codes. The matching gonna take some time. So like you just click it and let it run.
I'm sorry, before we go to matching,
Yeah.
the treatment grid cell, it's a grid level observation for grids which have Demi-lune in it.
So yeah, the treated grade has the Demi-lune in it. But like
And then it's one observation per year per pixel, or is it two? I see there are multiple observations per year for the same pixel ID.
yes, because the whole studies here is we got the outcomes from 2010 to 2025.
Right.
Because during this period, what we found is that those clusters, those Demi-lune clusters, actually are constructed at different time. So that's why we use this standard the idea analysis to do it. So yeah.
Preceding for you.
3 season per year.
Yeah.
Okay. And 3 season is dry after, dry before.
Mm-hmm.
Right.
Yeah. So like we will run the matchings. Yeah, it will take a few minutes to run the match because it's gonna loop through each clusters. So what we should expect to see is like we have 25 clusters in total, and then at the end, we should have 1,105 matched comparison cells. Let me know if you finish this step.
And we are matching on what, sorry?
We are matching.
KPIs?
Huh?
How do we match?
We're matching using the nearest neighbor algorithm, which means we are finding the most similar grid comparison cells based on the pre-treatment change of NDVI and NMDI.
Okay, the NDVI.
Yeah. So like when the matching is running, just let me know if you have any questions on what we just taught. And if that, yeah.
I got a nerve, but I ran for me early, so. Maybe if we just leave with fire.
Oh, I didn't. You didn't just download the packages.
Oh, yeah.
You have to run the rest of it. Yes.
Oh, okay. So I installed them already.
Yeah, you have to run.
Yeah, sorry, forever I do the same thing. But I did it all the more.
So after that, you run it. It's up. Run it.
I use this on strats.
It's running? It's running. Okay. Yeah. The result is because we went now within the resolution of the okay. So some result I lost and yes, so it or some method that you that's and then that is all levels.
Yeah, even just some stuff.
Just like that's it. So like at the end of the matching, you should expect to see like 1,105 selected comparison cells at the end when it's finished, right? Great. So after we have those selected comparison cells, we're gonna prepare a panel dataset for our DID models. So in that dataset, we're gonna filter out the gray cells only in the rainy seasons because the Demi-lune is designed to capture the rain waters. So we expect to see the strongest distinction between the treated and the controls during the rain seasons. So that's why we only filter out the rain seasons indices in this case. Yeah. So this code help us to filter out the rain seasons only. And then the next step is that we want to build up the treatment years for the comparisons and treated. So the treatment year is very simple. It's just the first year we found those Demi-lunes on the images. So let's go back to examples here. So on the images from 2014, we didn't see any Demi-lunes on those images. But the next image is from 2016, and then we found those Demi-lunes here. So the treatment areas for those Demi-lunes, the treatment year for those Demi-lunes will be 2016. And then for the comparison cells, the treatment year will be infinities because they've never been treated yet. So we just use the infinities here to represent the treatment years. After that, the models will automatically calculate the event time for us. The event time is how many years before or after the treatment time. So if the event time is negative, it means like year before, like pre-treatment. If the event time is positive, it means the years after the treatment. And the next step is our primary models. And compared to the normal DID, it will bias our studies. It's because our Demi-lunes, they're constructed on different time. So the treatment effect maybe varies, like if you construction time is different. So that's why we use this Sun and Abraham estimators here. So we're gonna use the false and SUNAP functions to carry out this estimator. And then the estimator just help us to estimate the dynamic treatment effects by cohort at event time. And then it also compared the treated grids to those grids that has not been treated yet. Wait, let me resentence the whole. Okay, so the estimators will compare the treated units only against not yet treated units. So in that way, it will like help us to not bias by the treatment time here. And then compared to the regular model design, we added a bin relative time here. It's because for the event time is calculated, if the event time is smaller than -5, it's only one treatment time in that cohort. In that way, it will be biased by one treatment time. And then it's a similar reasoning here why we bin any values greater than 5. And also we added a year and the grade ID fixed effects here. In that way, we account for some spatial and temporal effects on the Demi-lune. And then we also cluster the standard arrow by using the cluster ID because those Demi-lunes are spatially clustered. And then so let's run the chunk, the code chunk for the standard DID. Before running this, you have to make sure you run the preparations chunk first, and then run the Sun and Abraham code.
So I mean, according to your experience, is this SAS package the best right now? No?
That's a good question. So like I think this is the false. That is the most common two-way fixed effect packages in R. And then they have this SUNAP functions which carry out the Sun and Abraham estimator. So I think this package is like most commonly used right now, or if you run this estimator. Is that right, Ariel?
It's one of the more common ones. It's also like Callaway and Santana and a bunch of other flavors.
Yeah.
This one uses the never treated sites, so all those comparison sites that we match to. Kind of the way that you'd expect it. So for every time period, the comparison group is those that were never treated and those that are not yet treated, and we can combine them pretty easily.
Yeah.
But you can pick your favorite flavor and do so much of other options.
There are other estimators gonna use like different packages.
Yeah.
Sometimes too many packages is scary, no?
Yeah.
Repeating like.
Yeah.
Yeah.
They're now pretty easy to read. This is only a few markers.
Also, you can try to run other estimators as a robustness check, I think. To see like
You will almost certainly have to decide.
Yeah. Okay. So after we get the models, we will use it doesn't work again. Okay. No, that. Okay, great. So after we have the models, we're gonna use the summary functions to give us the outputs from the models. We also use the iPlot functions so we can visualize those outputs. So after the summary functions, you should see like little text summaries of what we can get from the models. Some important factors in this table is that we have these negative values. Those are the pre-treatment coefficients. So we want those pre-treatment coefficients to be close to zeros. So in that case, it indicates that we have this pre-treatment parallel trend assumptions meet. And then that's why we have this NDVI. expect to see is near the zeros here. And then the coefficient with this positive value, they are post-treatment coefficient. And I'm gonna read it out what those coefficients mean. And I want to make sure we have the correct definitions here. Okay. So for the coefficient, they actually represent the estimated differences in outcomes between the treated and comparison grid cells at a given event time. So what it means that it actually tell you like if the outcomes is smaller or bigger, compare our treated cells to our comparison cells. So in that case, we have these positive values for the NDVI, indicating that the NDVI values in the treated grid cells is actually larger compared to our comparison grid cells after the treatment. So this represents that the vegetations in the treated areas actually is greener than comparison grid cells. So for example, we have this coefficient of 0.02 in the years or 4 years later after the construction of Demi-lunes. It indicates that compared to those comparison grid cells, the NDVI in the treated areas is 0.02 larger than what we should expect. 0.02 of NDVI seems to be small because we know the NDVI range is from -1 to 1. But the average baseline in this area, the average baseline NDVI in this area is 0.18. So it's a really small number. And 0.02 increase is almost like 10 to 12% increase of NDVI in this region. So it's relatively a great increase of vegetations. And then we can, yeah.
What is year zero again? Year zero is the first time any Demi-lune was created.
So the zeros indicate the treatment time. So it's the year we found those Demi-lunes on the images. And then 1 year is like 1 year later we found those images. And then the thing they use 0, 1, 2 instead of like the actual year is because they kind of average the whole effects together. Because we know those Demi-lunes, they are constructed on different time, right? So they separate those in different groups and calculate the treatment effect for each group and then average the whole treatment effects together. So that's why we have those 1, 2, 3, 4 instead of the actual treatment year.
So for a pixel which never had a Demi-lune on it, but what year would it remain? Year would it be?
It will be infinite because it's never been treated. And then it just for comparison. Yeah.
So the comparison is between a pixel itself from when it did not have Demi-lune to add Demi-lune.
Well, it's
also pixel which never had.
Well, it's like now it's like compare the treated cells, which the grid cells have Demi-lunes, to not yet treated grid cells. Is that contains grid cells does not have Demi-lunes yet, as well as those grid cells never have Demi-lunes yet. So it's a combination of both. Yeah. So for the drought index, we can see a decrease here for the drought index. So a smaller NMDI actually indicating more soil moisture. So this represent that the soil moisture after the Demi-lunes actually have is get better. So after we have a result from our models, we should never stop here because we want to know like can we trust those results, and that's why we have to run like all different type of robustness checks here. And then the first robustness check we want to run is called the spatial spillover test. So like the primary concern for the spatial spill test is that some untreated comparison cells that close to Demi-lunes may indirectly improve by the moisture in those Demi-lunes, right? Because we know like the soils under the Demi-lunes, they got waters, but like water in the soils can dilute to anywhere. So like for those untreated comparison cells that nearby the Demi-lunes, they may indirectly improve and capture those moistures. So that's why we divided our grid cells, actually the comparison grid cells, based on the distance they from the Demi-lunes. Here we divided them into two groups. One is the distance is smaller than 300 meters, and the second disband is from 300 meters to 600 meters. After we divided those into two groups, we will rerun the whole DID model again to see what we can get. So I will pause here for a few minutes and let everyone to run the first robustness check. So after the first models, we also ran the next code chunk, which will help us to give those two figures. So that is the result of our first robustness check. We don't have any questions, we'll run into
Are
Arid.
you gonna walk through how to interpret this three?
Yeah, we're gonna interpret this later.
Okay.
Yeah. I just want to make sure everyone have this figure first.
Sure.
Yeah.
When you said the
Mhm.
description here, if
Yeah.
nearby comparison cells partially benefit from Demi-lunes, does that mean like a Demi-lune starts constructed there, or what do you mean to partially benefit from?
It's just like so for example, we have a grid cell comparison grid cell that is very close to those Demi-lunes. The water like absorbed by
Water,
the water there is probably gonna like improve the soil. Yeah.
So it's not necessarily capturing like
No.
if a farmer in a different area saw that their neighbor was doing Demi-lunes.
No.
Yeah.
It just because here we didn't include any household data here.
Yeah,
Like
right.
actually, yeah, it just spatially we identify those Demi-lunes and areas without Demi-lunes.
And then I guess it wouldn't have shown up as a untreated area either because it would have shown up as.
Yeah, exactly.
Alright,
Yeah.
okay.
Mhm.
So still over in terms of moisture,
Mhm.
adoption.
Yeah. Has everyone got those two figures? Okay, so like let's interpret those two figures. So the first figures is the NDVI figures, and then what we can tell from this figure is that the whole result is divided into three parts, right? We have those smaller closer within the 300 meters, and then also the second group is 300 meters from 600 meters, right? If there is any spill effect, we should see like they are changed in different ways, right? But in our result, they are changed in very similar trend. So in this case, we can conclude that there are no spatial spill effect in our design, or there are very minimal spill effects here. And then same for the NDVI, we see that the three groups they actually change in very similar trend here, and it's not statistically significant different.
One question.
Yep. You have.
Yes, from back in the university, like the basic was to check like Moran's eye test on the residuals. Like here, we just check even the model, not of the result of the model, of the coefficient, rather than the residuals. Is any strategic decision for that?
I mean, I think in some ways it's kind of the same insight in that we're trying to look at a sample that has a differential exposure to the treatment. And the residual idea is to think about that within your like original sample and model it in the error terms. This is a way to try to just make that more explicit by splitting the sample into based on that same residual modeling of distance to treatment.
Just the other way around, the same method.
Yeah, I mean, the residual approach thinks about, are your standard errors too small because there's some clustering that's happening spatially, and can we model that to make sure that the standard errors are the right size? This is a slightly different question. It's trying to say, what is the extent of the spatial spillover that's happening to treatment, not on the precision of the estimates. Not are the estimates precise enough or too long that general.
Also, like, try to add the impact of the spatial autocorrelation in the model with cluster the standard error by adding a cluster ID.
So that's the way to make sure your standard errors are not too small, but that this is the way to try to understand if the treatment's spilling over to other nearby areas.
So after this is like one type of robustness check we can do, and then I'm gonna introduce another robustness check here. It's called heterogeneous check. So in that way, we want to know like if the environmental conditions are different, that the impacts of Demi-lune is also different. So for example, we can see like if the construction slope of Demi-lunes are different, will the treatment effect different? Or the elevations or vegetation conditions. There are lots of factors we can test here. And then just gives examples, I use the baseline NDVI as the the factor to test. The baseline NDVI will give us a baseline environmental condition of that areas before the Demi-lunes was constructed. So in this case, we want to know like if the Demi-lunes on some like more degraded areas is more effective than Demi-lunes on relatively greener areas or not. So in that case, we also divided the whole gray cells into two subgroups. The first one is the gray cells that above the median baseline NDVI, and the second is below the median NDVI. So in that case, we have a group that is relatively greener areas, and another group that is more degraded areas. And then for each group, we will also rerun the staggered DID again. And then just leave you guys some more minutes to run the models, and then also run the iPlot chunk. So we will get those two figures. So like in the code, if you see like we use the year of 2013 as the baseline, that is because all the Demi-lunes we digitized, they actually constructed after 2014. So 2013 here is like a very conservative choice of baseline year we used. Does everyone have these two figures? Great. So let's rate these two figures. So similar with the spillover effect, we also have three subgroups or three groups here on this plot. The black one is the group below the median NDVI, which means the demi-lunes on more degraded areas. And the red one is like above median NDVI, which means those demi-lunes on relatively greener areas. And then also the original whole data set. So in this case, we found that the NDVI, some of the pre-treatment are slightly different because they actually have different baseline conditions. But like for the post-treatment coefficients, they are changed in very similar ways. So in that case, the baseline NDVI does not have very significant impacts on whether the demi-lunes on the treatment effects for demi-lunes on greener areas or more degraded areas. But the drought index are very different here. So like for the black line, we can see the post-treatment effect coefficient, they are close to zeros, indicating that the treatment effect or the effect of how demi-lune is gonna improve the soil moisture is relatively weak in those black groups, which is like more degraded areas. And then for the red groups, which is greener areas, we see that the demi-lunes actually capture more water or more soil moisture here in those groups. Some possible explanation here can be that, for example, if we have some like pre-existing vegetation layers, when we have waters captured by the demi-lunes, the vegetation can play as a role of like cover or shade areas, which help the water to retain a longer time, right? But like for exposed soils, that does not have a vegetation protection here. It just can easily evapotranspirated by sunlight or higher temperatures. So that's why the effects of whether demi-lunes will improve the soil moisture is weaker in the degraded areas. And then there are also like other types of robustness check we can run. For example, we can loop through each clusters to leave to delete it or remove one cluster out to see rerun the whole analysis again using the 24 REST clusters. By doing that, we can see if the treatment effects they are driven by one major clusters or not. And then the result is that it doesn't driven by any major clusters, but because that loop will take a long time, so I didn't include it in our hands-on sessions. Even though I figured out like we have some very longer time to do that kind of analysis. But basically that's all for my hands-on session. And I actually ended very early. Yeah, so there are some takeaways. It's basically the major results from our model indicated that the demi-lunes can provide and sustain impacts on the vegetation greenness and also the soil moistures. Also, like matching and meeting the parallel trend assumptions are very important for the idea analysis. And then after this hands-on session, I hope everyone can know like what is the stagger DID and how we can do it in the future. That's it. Oh, question time. Or I guess like they have some times just to have
I guess
pause.
you're welcome to chat and
Yeah.
but can I ask you to reflect on one thing?
Mhm.
So, you did not go to, in grad school, you did not learn anything about differences in different standard designs, right?
No,
Like, that was learning on the job.
exactly.
So what was the most surprising or like, I don't know, what was your experience like learning causal inference? Coming from a GIS and environmental science background that you want to offer to other people as encouragement for what you're doing?
That's a very interesting question because I just talked with someone in lunch today, and then he's also like a very remote sensing expert instead of economist, and he's questioning that, look, why do we need a counterfactual? So if you can see the NDVI changes in time series analysis, why do we need a counterfactual? I think that is like the most significant question I will question myself like during this job. Like why do we like spend so many times on like pushing the reasonable comparison cells here? So I think it that because in the real life the mechanism can be very complex. There are lots of confounding factors can influence. For example, the Demi-lune here, the precipitations can definitely improve. It impacts whether we have like more vegetations or not, and then also the temperatures. So like the reason why we select a counterfactual is that we want to make sure those impacts or the effects we see, those increase in the vegetation greenness is truly come from the Demi-lune instead of other factors. So that is like the major takeaways from myself during this job. Yeah. Yeah.
Good question
Uh-huh.
is how is it different and this classic engineering problem. So I see that the Demi-lune that constructed. So looking at the last slide, robustness tag, I think
Mm-hmm.
in some cases there is some idea that Demi-lunes are constructed where people think there is a potential of improvement or something like. I wouldn't construct a Demi-lune in a place where it will not store water in it, right?
Mm-hmm.
So I think that it's not. So this improvement. So we construct. So if I say that okay, I construct a Demi-lune and then my vegetation index will go up.
Yeah.
But I will only construct a Demi-lune in an area where I think the vegetation will go up. Right.
Yes.
So there is this problem. I don't know. Some of it is being addressed because we are looking at vegetation index before as well, and we see that there. Even if we look at low vegetation index zones, the improvement is still there, but it's less elaborate than we're there. So that's one question I'm fully addressing for this endogeneity problem where we construct Demi-lunes where we think it will work best or where they are pushing effective. Thus, I'm constructing it here. And then also there has to be this maximum number of Demi-lunes you can construct in an area. There are already 5 Demi-lunes. I want to construct a 6th one and expect similar linear increase in vegetation, and that's all positive. Maybe at some point after 6, if you construct another one, then it won't add anything to the vegetation. So, is there? Did we talk about this? Did we?
Okay. For the first question, I think the reason why we have this robustness check is not from a practitioner perspective. It's more like after we have the model result, we found that the baseline NDVI is quite different in those grid cells. So we want to know whether they have the impacts here. So that's why we divided them into 2 groups. And then the results for the vegetation is that it actually have no impacts, right? So they have the similar trend, similar increase for both groups, right? But the soil moisture is actually different. So that is like what capture our interest, and then can go deeper into like how to find like what is the main reason causing this different, right? It can be like a further analysis here. And then for the second questions, the number of Demi-lunes, I think that is very important. And then what I didn't mention is that for the treated grid cells we select are only the grid cells contain more than 22 Demi-lunes in that grid. So that is because according to some like practical guidelines from the Niger government, they have optimal densities of Demi-lunes. So they have like some guidelines like to teach the farmers how to build those Demi-lunes, and they have like optimal distance between the Demi-lunes and then the size of like optimal size of the Demi-lunes. So in that way, we have optimal densities we should expect to see on each grid cells. We included the grid cells have more than those optimal densities. So in that way, we can make sure that this grid cells is full of the Demi-lunes. It doesn't include other areas, for example, the cropland or like some other confounding factors here.
Yeah.
Yeah. Yes.
It's kind of certain context of the Great Big Law.
So
Are these dendrils in the context of the Great Big Law?
well,
With the Great Big Law should the border free.
The Demi-lunes, they are. That's back. Do I have like a picture of how the Demi-lunes looks like? I think. Yes. So the Demi-lunes basically they kind of like dig a half circular, I wouldn't say hole, but like areas that have a lower depths than the other areas. So in that way, they can capture water in those holes.
And this was done under a specific project or?
I think first of all, there are common practicals for local farmers to do it, but also I know there are lots of organizations funded those projects.
I think they're meant for annual crops, they're not meant for. Some of it, you can see some of the background is like woody and like tree cover or more permanent cover, that's typically what the Great Green Ball was trying to promote. And like, that is a little bit separate from these construction.
Yes.
Two questions. One is the opposite. From an economist who wants to get into remote sensing and improve the model. So if you have any insight on that side. And the second one is linked to the colleague just proposed, but is the model easily like we can use the same approach, but we want to create other covariates to control that we have an idea we need to control for other things like you mentioned rainfall or proximity to urban settlement or any human settlement. Some nonlinearity is possible or the model would run the same. So thank you.
So for the first question, I feel like I'm not the right person to answer that because I'm not from the economic school first. Like I never learned economics before this job actually. So I'm.
But hang on.
Yeah.
Why don't you just explain all your data preparation, right? The part that you skipped over again. Ask you hand label. You hand labeled everything. And then you put it through Google Earth Engine to process. Just describe that part in a little bit more detail, because it's not that
Right.
it's
So.
doable even for economists.
Are you sure?
Yeah, I think it is like first of all, the Demi-lunes they are easily identified on the images, right? There are lots of open sources, high resolution images you can use to locate those Demi-lunes. So basically, the images I use they are from the Google Earth Pro or Google Earth satellite images, and then I imported those imageries into ArcGIS Pro. So ArcGIS Pro is a software to run some geospatial analysis. And then in the ArcGIS Pro, it's very easy for you to digitize the point. You just use the mouse, click, 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 and that's it. It's very easy and hands-on. And then
at ArcGIS Pro, you can use QGIS.
Yeah. So because ArcGIS requires some license, you have to buy it to do some like run some advanced analysis. But QGIS is an open source software. There are lots of add-on on QGIS. And then after that, those little square grid are easily to generated in ArcGIS Pro, and you just randomly generated some grid cells with 30 meters. The reason why we choose 30 meters because we want to match with the Landsat imagery pixels. Those pixels are 30 meters wide. And then we just ran analysis called zonal statistics, which will automatically calculate how many dimensions within this grid cells. And then after that, we just export the little grid cells into Google Earth Engine, which is another platform where have a lot of imageries. Because we ran the whole analysis from 2010 to 2025. It's like 15 years. If we download all those images, the computer is gonna blow up, right? So that's why we use the Google Earth Engine, which is a cloud storage based platforms, so you can get the images quickly and then calculate the NDVI, the MDI levels. And even though the code can be a little bit complex in Google Earth engine, but there are lots of available resources for people to learn like how to calculate it NDVI, because NDVI is really commonly used indices.
Including on our GeoField.org site, there's a
Yeah.
resources tab that has a code and tutorial for how to calculate NDVI in Google Engine. It's totally doable and it's totally free. So Google Engine access and all the underlying data sets are free, right? ArcGIS Pro is the only actual software that we use. We take.
And I think R has a package as an interface for Google Earth. So
Also, like for all the geospatial analysis, you can also run it using Python or R. There are lots of mature packages in Python or R that can handle all those kind of analysis.
which is quite for an entry level can be quite challenging. You get used to one software and have to learn different one. But now we have AI, it's easier. But
Yes, that's
what's
what.
your intake of it? Should be open mind and be ready to use different languages and different software, but there is one that's better to specialize in one.
Yeah. Or you have another choice is to hire students. Hire like a person who can carry out like all those geospatial analysis. Yeah. You have a second question? Oh, the robustness check. Oh my god, I almost forgot it. I think for the like, do you still remember the question?
Yeah, to get back variance to the model and
Yeah.
would the code change or there is something else that we have to take into consideration or basic or
Exactly. So like there are also like lots of other factors that probably can like influence the result here. So for example, we have slopes and the elevations of Demi-lunes. What else? It can be like the distance from the Demi-lunes to the closest villages or like communities, because the potential hypothesis is that if it is closer to the house, people can easily to maintain those demos. So we should expect to see like a longer impacts of those demos. We try to run those robustness check, but the thing for the distance to village is that we have to find those village first. There's no available data set of like the location of villages in Niger yet. At least I didn't find it online. And then there's some like I tried to find some like administrative boundaries or like some possible data set. But it didn't give us a very reliable results from those data sets. So that could be a factors. But yeah, if we have like more data set, yeah. Yes.
Yes, sorry, can I ask a question? I'm just wondering if this sort of methodology is sort of the same sort of methodology you follow for other kinds of interventions, like the majority of it. I'm just wondering how easy it would be to kind of adapt these scripts and methodology for other kinds of interventions. I think it was touching kind of partly I was better, just wanted to clarify.
Yeah.
Like say it's like canal rehabilitation, for example. How easy would it be to adapt those scripts? Is it mainly the first part where it's like the identification of the actual intervention which would need to be adapted, and then the rest would be quite a similar workflow, or I don't know if we should go into that.
Yeah, so like definitely the first thing you need to prepare is the whole remote sensing indices, because I didn't like that can be quite time consuming to calculate those indices. And then the first part, like calculate treatment time. That thing is that is very case specific. So like if you change to another project, the definition of treatment time can be different. Yeah, so it's really depends on like what project you carry out and like how do you define the treatment time. And then the staggered or the certain Abraham estimator, I'll try to find it. So like, yeah, so the basic model is this part. But like the special thing we did is that we bin the relative even time. So probably in some other project you don't need to do this step, right? And then we also add this fixed effect. Also, we cluster the standard errors. So that is some additional part we have on this basic models.
But
Yeah.
then it's-
Yeah. So like this basics model you can carry out on your own project, right? But like some specific as-on part is really project specific, and like it depends on what your research question is and your research scope. Yeah. Mm-hmm. Any question?
Again.
Yeah. Right.
We can hang out for a little bit and then at 5 is the cocktail reception.
Yeah.
Which time? On average, it's super.
Yeah, I should like divide part after part.
Yeah.
And I was spent this. Like none of those. God, it's kind of like the.
Hey.